Okay, hi everyone, and thank you so much for joining us today for this week's session of the Parks College weekly webinar series. My name is Amy Price, and I'm the outreach coordinator for Parks College. I'll be joined today virtually by Dr. Mitchell and current engineering student Joe, who will be showing us around the computer engineering program. We're very excited to have you joining today from wherever you are. Thank you for taking the time to virtually visit us and learn more about the aviation and engineering programs at St. Louis University. In total, Parks College has programs available in aerospace, biomedical, civil, computer, electrical, and mechanical engineering, as well as flight science and aviation management and physics. We hope that you'll see or hear something today that piques your interest. Before we begin, I wanted to give you an idea of how this webinar will flow. In just a moment, I'll introduce Dr. Mitchell, who will begin with an overview of the computer engineering program. He'll then introduce Joe to share his perspective as an engineering student. And during the last few minutes, we'll open it up for some question and answer time. Throughout this webinar, we do encourage you to submit any questions you may have to the Q&A feature at the bottom of your screen if you're viewing through Zoom, or in the comments section if you're viewing through Facebook Live. And we'll do our best to answer as many questions as possible during the last few minutes of our session. Throughout the webinar, you don't need to worry about turning off your microphone or camera. You can hear and see our presenters throughout the webinar, but we cannot hear or see you. This session will be recorded and posted to our YouTube page in the next few days, and you'll receive an email with that link when it becomes available. If you would like to view any of our previous webinars, you'll also find those recordings in a Fall 2020 playlist and a Spring 2021 playlist on our YouTube page. Okay, so with that information out of the way, I am now very happy to introduce SLU's computer engineering program and Dr. Mitchell. So Dr. Mitchell, I will let you take it from here.
Hello, and again, thanks for coming to learn about computer engineering. My name is Kyle Mitchell. I am the program coordinator for electrical and computer engineering. Today we are going to talk about what computer engineering is in a little bit of detail. Hopefully give you some insight into what this is and how it's different from other things you might be thinking about. And we are also going to give you a little bit of idea of what kind of work we do in computer engineering here at SLU. So that being said, let me get started on a presentation here.
Dr. Mitchell, you should have sharing ability now.
Thank you. All right, so computer engineering is the discipline that exists between electrical engineering and physics with quite a lot of comp sci in it. So depending on which way you're going with computer engineering, we do a lot of solid state electronics. So that's the semiconductor part, the integrated circuit design. We also do a lot of stuff with programming the computers that we build. So it sits right between those traditional areas of comp sci, physics, and electrical engineering. We build the computers that don't interact with humans very much. So when you think about the computers in your car, the computers in your TV, the computers in your toaster, the computers in your robots, those computers are the computers that we build. When we talk about programming, we program the similar type of computers. So the computers in your drones. So that's the kind of area that we're talking about when we talk about computer engineering. So it's everything from how do we get information into a computing system from sensors through the amplifier subsystems, into the programming, into the designing of the computer, and into the packaging of those computers into possibly harsh environments. So we deal with broad areas that consist of things in this nature. So embedded system design, that is the computers I just talked about. So the robots, the TVs, the microwaves. We deal with information security. So how do we make it so that the web is secure for you to use? But beyond just the web, how do we make it so that your hard drive is secure? How do we make it so that information that you put places only you can read, or only those people that you want to can read? We deal with a lot of robotics. So all of the processing, the sensing, the electronics that do the control, we do a lot of that stuff. In the information security area, a lot of that deals with cryptography. So we do a lot of stuff with cryptography. Um, we do a lot of stuff with how to store data. So when we talk about things like the Genome Project and medical health records and other big data sets, the ability to build large storage devices is something that we do. Um, we deal a lot with how do we design the next processor? How do we design the next graphics card to make them faster, better? So that's the whole computer architecture part of this. Computer networking is a very exciting topic right now. As networks get faster, we continue to have to redesign the way they work in order to keep them working. So everything around making your cell phone be able to reach the internet, making your TV be able to reach the internet, making Google be on the internet, all of that back-end networking stuff. And then of course, the integrated circuits. Um, so that's kind of the big broad areas of computer engineering. So if you looked at that, I kind of separated those into computer hardware and computer software. We deal with both and we deal with them together. So let's look at what we mean by computer hardware. So fundamentally, everything that computers do can be boiled down to three operations on the numbers ones and zeros. So ones and zeros being the binary language that computers understand. If we think about the operation of AND, where we look for whether the two numbers are both one or not, we think about the operation OR, where we look at whether one of them is a one or not, or maybe they're both zero. And we look at the operation NOT, so the inversion. So we change the one into a zero. Everything that computers do can be broken down into those three basic operations. This is a way we used to depict functionality of those three operations. So this particular circuit can add three ones and zeros together and come up with an answer. We call it a full adder. It's a fundamental building block for a lot of different things in computers. If we were going to try to build this circuit, we would end up with something that looks like this. So those little black chips, each one of those little black chips has about 6 of those gates in it. So one of them has 6 AND gates, one of them has 6 exclusive OR gates, one of them has 6 OR gates. We put this is a breadboard. This is the way we used to prototype circuits. Lots of messy wires, lots of potential for problems. But if you look, you can see that on the left-hand side, I have put a 0, 0, 1 in, and I have gotten a sum of 1. And on the right-hand side, I've put a 1, 1, 1 in, and I've gotten a sum of 3. So the red numbers are not a bigger binary number than just 3 individual binary numbers, but the green numbers are the green lights are a count in binary. So we think about those as a combined set. So a 0, 1 would be a 1, a 1, 1 would be a 3. All right, we don't build binary circuits like that, or we don't build digital circuits like this anymore. They've gotten too big and too complex, and it would take shelves of chips this size to do anything meaningful. So we now use things like the little chip in the center of this board. This is called a field programmable gate array. This is one type of integrated circuit. This particular one is manufactured to be changeable in the field. So this is really nice for learning with, because you can program stuff into that chip. And if you don't like what it's done or you've made a mistake, you can change the program that's in that chip. If you get it correct and you want it to be cheaper and faster, you would then spin this into a chip that can't be reprogrammed, a full ASIC. But for what we do in most educational circumstances, we stop at this level. Now, the nice part about that chip, I showed you 3 chips on the previous slide that each one had about 6 gates in it. This chip has about 40 million gates in it, right? And it has the ability to wire those 40 million gates in a lot of different ways. This is the way we build build digital systems today, is we build them out of very large gate semiconductors. And by large, these are actually kind of small. So what I did is I went and implemented that ability to add 3 bits together. And if you look at the top left here, the 3 switches on the right represent those 3 inputs again. Actually, I made it bigger. So rather than just being 3 inputs, this one actually adds a pair of 4-bit numbers together along with a third carry in. So if you look at this, I'm adding 3 and 3. And if you understand the light pattern, I'm getting 6. If you don't understand the light pattern, that's okay. We're going to fix that on the next slide. So in the next one, or in the bottom right there, if you look close at that, I'm using all 9 switches. So I'm adding 15, 15, and 1, and I'm getting 31. So as you go through electrical, or as you go through computer engineering, we're going to teach you how to build bigger and more complex things. So this is an example of how to build a bigger and more complex thing. It's not very much bigger. We've just taken 4 of those circuits that I showed you to start with and cascaded them together so that we can add bigger numbers to. The next thing that I'm going to show you to make this bigger and more complex is to make it easier for humans to actually tell what's going on. So notice I kept the circuits the same. In that top one, I'm adding 1 and 1 and getting 2. If you pay attention to that green light, that's a 2. And then the other one, I'm adding 15 and 15 and 1 and getting 31. But most humans don't like looking at binary lights and trying to determine what's going on. So I have changed this so that instead of outputting binary, it outputs decimal digits. There's quite a lot of knowledge that goes into trying to use ands, ors, and nots to convert binary numbers into decimal numbers so that they can be displayed in this fashion. Again, I'm just trying to demonstrate here that we're going to teach you how to build bigger and more complex systems. With the next slides, the systems get very big. So these slides I'm showing you now, these are things you would do as a freshman or a sophomore. When you get to be a senior, you're going to do things like this. So these are very large, complex schematics. Just like I told you, we don't wire things on breadboards anymore. We don't typically draw circuits like this anymore either. I had the computer generate these from a design I was doing just so that you could look at how big and complex these things were. The design is actually entered in something that looks like source code. So we actually describe computer hardware in programming languages like VHDL and Verilog. This is some VHDL source code. So we don't actually draw great big huge schematics and try to get it right the first time. We write software looking stuff, we simulate it, and we hope that it's right the first time still. Now what do these two things do? That's what we're going to show you on this page. So both of those schematics play Pac-Man. Hopefully everybody recognizes Pac-Man. You should notice that these two Pac-Man games play slightly differently. They play slightly differently primarily because they are implemented in very different fashions. So the Pac-Man that's running on the left, that entire game is written as a very large collection of ands, ors, and nots. The entire Pac-Man, all the numbers, the graphics, the movement, the logic, the ghosts used to move around, it's all collections of ands, ors, and nots. So we can do very complex things with these ands, ors, and nots. But sometimes it's not very convenient. So the one that's running on the right, I changed about 85% of those ands, ors, or nots into software. So inside of that chip, I put down a processor. And in that processor, I wrote code to do things like keep track of where the ghost should be, keep track of where Pac-Man should be, keep track of what the score is, move the images around. So the only thing that's not being done in software is actually drawing to the screen. All the rest of it's software. And this is just an example that hardware and software are pretty similar in their ability to do things, but the convenience changes a lot. And since that convenience changes, how to actually keep score in decimal is much easier to do in software than it is in hardware. One one of the things that we teach our students is how to make the choice of what belongs in software and what belongs in hardware, and how do you get those two things to communicate with each other. So when we talk about writing software, I told you that we typically do things in computers that don't interact with humans very much. So the computers that we play with look fairly different. If any of you have played with a Raspberry Pi or with an Arduino Uno, these should look a lot like those types of computers. Um, these are the same processors that are in those types of computers. So we play with computers that are really meant to interact with the world and not with humans. Um, and it takes a little bit of different knowledge to program these, um, primarily because we actually read things from the IO pins and write things back to the IO pins. So when we talk about teaching you how to do software, we're going to send you to learn how to do some software from the comp sci department, and then we're going to add to that ability so that you know how to actually program chips that don't have a keyboard and a monitor and aren't producing some type of human usable information, but instead are interacting with other mechanical and electrical systems. So by the time you're a senior, you will have done quite a bit of software. You would have done quite a bit of hardware. We're going to turn you loose with a board like this to do some type of larger project. This is where we bring back together, how do you do a project that has both hardware and software on it. So if you notice, this board has a lot of things you'll recognize from a normal computer. It has an HDMI connector, it has a keyboard connector, it has an Ethernet connector, but it also has a bunch of stuff that you wouldn't recognize from a normal computer in that it has a lot of IO pins. So underneath that heat sink in the middle is a somewhat larger FPGA, and this somewhat larger FPGA has those same 10, 15 million and or not gates on it, but it also has a gigahertz processor and a bunch of memory. So this computer is specially designed so that you can do custom hardware design and custom software design in the same chip and make them cooperate on solving a problem. So recently I've used this board to build a demonstration platform for the National Geospatial-Intelligence Agency, to give them a concept for what they might use for their desktop computing going forward. They want to be able to have desktop computers that don't have any storage at the desktop. All of the storage takes place in a secure server room, in the basement or in the attic or someplace else. And that way, if these computers walk around, there is no information on them to walk around with them. So that's the kind of thing you might be able to do with this type of board. This is the same type of board that's also found in, if you have some type of cable box that tunes your TV, it would be that. This is the same board that would be in your TV. This is the board that would be in the entertainment system of your car. So this board has a lot of places it could end up, where it could be doing a lot of audio video type stuff. So what do my students work on? My students work in a lot of places where we collect data and do something with the data, along with some of the other stuff that I've shown you already. So I put a quadcopter on the left side of this picture. We have 2 or 3 projects we're working on right now with the aerospace department, where we are helping them collect data to make drones safer. Right now, small drones like this, and even drones that are a little bit larger than this, if they develop some type of mechanical problem, if one of the propellers breaks, or if an arm breaks, these things pretty much fall out of the sky like a brick. But they don't have to. The only reason they do is because they're not smart enough to not. Um, there are demonstrations of ones that you can turn a motor off, and a quadcopter like this can continue to fly well enough to set itself on the ground. So we're helping them collect data on how to detect if a quadcopter has experienced some type of damage in the air, and we're helping them collect data on what to do about it. So that's one of the projects we're working on is we're collecting a bunch of data for our aerospace colleagues to make drones safer. The picture on the right here, this is an articulated arm. We do quite a bit of work with robotics in our department, um, quite a lot of different robots. But this particular project is we are putting this articulated arm on the internet. We're using a Raspberry Pi to put this on the internet in such a way that we can give homework assignments, programming this arm to do certain functionality and allow that to be done remotely. So allow that to be done web connected. Now that could be for our students in particular homework assignments, or that could be just anybody from the general public that wants to come see how you manipulate an arm. Or it could be for grade school students that are doing some type of STEM experiment. We're not particularly sure where this is going to end up. We're just in the initial stages of developing the web interface and web tools for being able to do this. These are some additional data gathering instruments that I've designed and my students have designed. So the one on the left, this is designed to listen to bridges and hear them crack. So when metal undergoes aging fatigue and corrosion fatigue and it cracks, cracking makes a very particular sound. Um, if you've ever torn a piece of paper, you know that tearing a piece of paper makes a very particular sound. Well, tearing steel makes a very particular sound. And this board is designed to listen for that tearing of steel. This was a project that we worked on with the civil engineers to see if we couldn't, in a somewhat low cost electronic system, hear damage in structures happening. The one on the right does something fairly similar. So this is a board that measures the vibration of structures. So along with making a particular sound when they tear, structures shake at a particular frequency. And if they lose mass or develop cracks, the frequency they shake at changes. And this particular instrument is designed to measure the frequency that structures are shaking at. The board on the left here, this is a board that one of my students designed about 10 years ago. At SLU, we have a very active satellite program. We launch a satellite into space about every 4 years. This was the mission board for the satellite about 10 years ago. So this is an infrared camera that we put on a 6-inch by 6-inch cube and NASA launched into space for us. And that's probably 20% my design and 80% 3 or 4 students that were working with me's design. So we actually put working hardware in space. The board on the right, this is a board that a student of mine worked on that we were trying to measure, that this was a company that hired us to help them measure one of their sensors. So there's a company that makes paint that has a particular resistance. And if you stretch that paint, the resistance changes. So we call these a strain gauge. It's the same type of sensor that we were using in the previous project to measure the frequency that structures shake at. But this particular board is designed to measure the resistance of paint that has been applied to some type of bridge or tunnel or building. All right, so that was a few of the projects that we are working on now or have worked on in the recent past. Let me show you around the building a little bit and talk to you about some of the spaces. So this is what we call the electronics lab. This lab has power supplies, function generators, oscilloscopes. This is where people who are interested in electronics go measure what it is they're trying to build. So all of the labs I'm going to show you today, with the exception of one, are open to undergraduate students 24 hours a day. We encourage you to come work on projects in these. We've had a number of students come through the program that have developed projects and gone on to start companies with the projects they've developed. So this lab, if you're doing something that requires electronics work, it's open to you. Come use it. Um, you'll take a couple of undergraduate labs in here where we teach you about filters and we teach you about capacitors and resistors and we teach you about amplifiers. This is the primary computer lab for the department. This is the lab where we're going to teach you how to program those small processors. This is the lab where we're going to teach you how to design the digital circuits in those FPGAs. This is also the space where the students hang out, do homework, eat lunch. It's a very active social lab for the students in the department. This lab's a little more boring. This is where the advanced classes in computer engineering are taught. This is where we teach robotics. This is where we teach you to build video games out of that board that looks like your TV tuner. Most of the stuff you're going to play with in lab is locked in the cabinet right now. But again, it's a space where we instruct, where we give lab material, and a space where you guys have access to the building to do homework and individual projects and whatever else you want to be doing. This is a space that we leave open to students. The reason it's a mess like this is because it's covered in the remains of student projects. This space is completely open for students to come work on, store the projects in the cabinet, do whatever they need to do when class, if they need in a lab and class is going on in the lab, they come in here. But it's just what we call a student project lab. We've outfitted it with similar equipment, and we come clean it up every once in a while when it gets to be too big a mess. But primarily, we just let the students do what the students want to do in here. Senior design is a class you'll go through eventually. This is a class where you'll pick a project of your own that you're going to work on for 8 months. So this is someplace where you're going to do something relatively large and relatively substantial. So we have a space devoted strictly to that. So this is a reconfigurable space. Most of the tables move. Whatever project of the day the seniors want to do something with takes place in this space. So then we have some special spaces where if you work on some of our research projects, you get to come work in these labs. So this is the lab that the student I have with me today works in most of the time. If you look in the foreground there, you'll see that little arm. This is a space where our students do those advanced projects that I talked about in the last few slides. In this particular space, we study how to sense data. So the sensor systems lab, this is where we build those bridge sensors and we build those satellite cameras. This space is where we build satellites. So like I said, about every 4 years, we get a satellite ready for launch. If you look in the foreground on the left of this, you'll see a cage structure. That's the size of the satellite that we launch. The satellite group is not tied to any particular class. It is an undergraduate club. So the only thing that the faculty do is design projects and get them funded. And then it's completely up to the undergraduate club to go about figuring out how to construct the thing and build it. They get lots of support from the faculty. We give them lots of ideas and push them in certain directions, but it's not our project. It really is the club's project to build these satellites. This is one of the places where we fly drones on campus. So I get involved a lot with the autopilot work with drones. Right now in this is an indoor space where we test certain activities with drones. It's much better to test them indoors before we take them outdoors. And that way we know that they're going to fail and they're going to fail in a way that we can recover from. What's going on in this space right now is the virtual control of drones. So we are taking Oculus Rift goggles and Leap Motion hand sensors and making it so that you can reach into the virtual space of the Oculus Rift and actually control the drone that's in the cage behind you virtually. this has a lot of advantage in that most drones in the future for commercial use will be flown beyond the visual range of the pilot, and the pilot might be in charge of more than one drone at the same time. And this gives them the ability to visualize and to interact with the group that they're controlling at the same time. All right, so that's more or less the end of my presentation. At this point, I'm going to turn it over to Joe. Joe is one of my seniors that's been working with me for about a year and a half now on a couple of different projects.
Hi, yeah, I'm Joe, as Dr. Mitchell said. I am a senior computer engineering student. I am involved with a bunch of the different projects that Dr. Mitchell pretty thoroughly went over. I'm also involved with other things on campus like intramurals. I studied abroad. I do some tutoring, and I did some work with both the satellite lab and SLU's rocket lab. So yeah, that's a little bit about me.
Awesome. I just want to thank you both for being here and use just the last few minutes to open it up for some question and answer. So if anybody has questions, feel free to put those in the Q&A or the comment section if you're on Facebook. Joe, I have some questions for you. I'm just interested to know what got you into this academic program, what got you involved in computer engineering, and what are your next steps after this?
Sure. So I have always kind of known I wanted to do something in the computer field. So I knew from high school I was either probably going into computer science or computer engineering. So it really was a choice between the two of those. I am more of a software focused person. So as Dr. Mitchell noted, that we do both hardware and software side of things. I often focus more on the software side of things. So that made that decision a little bit more difficult. But I also do enjoy the hardware stuff, so that was kind of what pushed me more towards the computer engineering side of things. I am graduating in May. I have a job in Madison doing software development for a company called Epic. That's my plan after graduation.
Fantastic. Yes, congratulations on your upcoming graduation. Dr. Mitchell, maybe this is a question for you. So you mentioned a lot of different applications in aerospace engineering and then into civil engineering with, working with structures and maintaining those out in the world. So it seems like there's a lot of collaboration. There's a lot of opportunity for entrepreneurs after academic programs. So what kind of jobs do our alumni go on to do?
So our alumni do a lot of different things. Just to drop a few company names, we've placed people with Amazon and Google and SpaceX. Locally, we've placed people with Anheuser-Busch and Express Scripts and MasterCard. They're doing everything from programming the guidance system of rockets and building the next big Google app to maintaining the financial records. So the people at MasterCard do interesting things with, I'm not sure the MasterCard people do, but computer engineers in general, they talk about high frequency training or trading in the stock market. Those are computer engineers and electrical engineers doing those types of things. They're doing it with some financial analyst watching over their shoulder, but that financial analyst has no idea how to make the computers work fast enough.
That's fascinating. Okay, Joe, last question for you. What advice would you give to a high school age student who's considering computer engineering?
I would say this is more of an advice for once you start, but I would say get involved early. One of the things that is hard to do is to reach out to your professors and ask for help, go to their office hours, things like that, especially in the first couple semesters when you're still kind of catching your groove. It sounds super intimidating to go into office hours and get help, or just get involved outside of class, but it's something that is completely worth it, and it's a huge benefit to you. And I've never once gone into office hours and had a professor who was angry that I was there to get help.
No, that is wonderful advice for any major, but I know especially in these engineering disciplines, getting some of that supplemental instruction is always helpful. All right, well, everyone, this brings us to the conclusion of our webinar today. I want to thank again Dr. Mitchell and Joe for sharing your time and expertise with us and sharing the computer engineering program with us. I thank you also to our viewers today. We hope that you did enjoy this visit to our engineering programs. And if you would like to learn more about the engineering programs at SLU, you can go ahead and visit slu.edu/parks. As always, feel free to reach out to us at our email address, parksevents@slu.edu, if you would like to connect further with us. And we welcome you to join us in this space again next week for a visit about robotics. So I believe Dr. Mitchell will be returning for that one. That will be Wednesday, April 7th at 4 p.m. So this concludes our webinar today. Thank you again for joining us and have a great rest of your evening.